All right, let's get into it. Today, we are going to build the architect's blueprint for systems that are truly, genuinely resilient on AWS. And we're going to be using Route 53, but not for the stuff you already know. We're going way beyond basic routing to find that one secret ingredient that makes your applications smart enough to know when they've failed.
So, here it is, the fundamental question every single cloud architect has to answer at some point. You've got your main region running, you've got your backup ready to go, but how do you make the DNS, the thing that tells users where to go, how do you make it smart enough to actually react when something breaks? Just having a standard routing policy, well, that's not going to cut it. And boom, there's the answer. This is the magic right here. It's not the routing policy itself that's so smart, it's the health checks that you attach to it. You can think of them as the nervous system of your DNS. They're out there sensing failure and triggering the reaction. This is the key to unlocking true DNS-level failover. Okay, so here's our game plan. We're going to start by making our DNS intelligent. Then we'll break down exactly what health checks are and look at the 3 different types you can use. From there, we'll see how they enable automatic failover. And then, this is a big one, we're going to talk about a caching trap that gets everybody. We'll wrap up with some pro-level architecture tips and pitfalls to avoid.
So, let's start with that absolute foundation. What are health checks? You've got to get this part because literally everything else we're going to build today, from a simple failover to a full-blown disaster recovery plan, it all rests on this one concept. So what is a health check in plain English? It's basically Route 53's way of constantly tapping your application on the shoulder and asking, hey, you still good? You healthy? It does this by sending little requests from a whole bunch of its servers scattered all across the globe. And based on the answer it gets back, or, the lack of an answer, it makes a decision. Now hang on, because this right here, this is a super important detail that trips up so many people. These checks are external. They are coming from the public internet, from AWS data centers around the world. Route 53 does not have a magic key to get inside your private VPC and poke around. And that little fact has huge consequences for how you design your network and your security. Okay, so if we're going to use these health checks, we need to know what's in our toolkit. And Route 53 gives us 3 different types of checks, and each one is designed for a specific job. Here they are at a high level. First, you have your basic endpoint checks. These are the most common, and they're perfect for checking on public-facing things like a load balancer. Then, you've got calculated checks, which are awesome for when your app's health depends on a few different things working together. And finally, the really powerful one, CloudWatch alarm checks, which let you monitor internal resources without ever exposing them to the internet. The endpoint check is your workhorse. It's the one you'll use most of the time. It can do a simple TCP check to see if a port is open, or it can make a full-blown HTTP request to a specific URL, like /health or /status. It's smart enough to check for a 200 OK response code, and it can even search the page for a specific word, like OK, just to be absolutely sure the service is up and running properly. Now, calculated health checks. This is where things get really clever. Imagine your application is only truly healthy if both the web server and the database are okay. A calculated check lets you do just that. You can combine other health checks using logic like AND or, so you can create one single master health signal that represents the health of your entire application stack. And this is how you solve that problem we talked about a minute ago. Remember we said the checks are external? Well, what if you need to monitor the CPU on a private database server? You can't just open that up to the internet, that would be crazy. So instead, you create a CloudWatch alarm that goes off if the CPU gets too high, and then you tell Route 53 to monitor the state of that alarm. It's a genius, secure way to get an internal health signal out to an external service like DNS. Okay, we've got our building blocks. We understand the different types of checks. Now, let's assemble them into our blueprint. This is where we see how all these pieces come together to create a powerful, automatic disaster recovery system. So let's walk through a typical failover. Step 1, something bad happens. Your primary load balancer fails its health check. Step 2, Route 53's global network of checkers detects this failure, and it happens fast. Step 3, Route 53 marks that endpoint as unhealthy and immediately starts changing its answers. Any new DNS queries that come in will now get the IP address of your backup site. And finally, Step 4, users are gradually and automatically shifted over to that backup site. Okay, so the failover is automatic? That sounds great. But is it instant? This next section covers what is probably the single most misunderstood detail about DNS failover. It is a trap that even really experienced architects fall into all the time.
It's a totally fair question. The health check failed, Route 53 saw it and reacted, so all my users are immediately sent to the backup site, right? The system is protecting them instantly.
Not so fast. The reality of how the internet and DNS works is just a little bit more complicated than that. Let's break this down on a timeline. At time 0, your main site fails. Within just a few seconds, Route 53 knows about it and updates its own records. But here's the trap. The DNS resolver on your computer or at your internet provider, it doesn't know about the change yet. It has cached the old, broken IP address. And it's going to keep giving you that bad IP address until its cache expires. That expiration time is controlled by a value called the time to live, or TTL. So here's the absolute key takeaway. Your real-world failover speed has almost nothing to do with how fast Route 53 detects the failure. It has everything to do with the TTL value you set on your DNS record. If you have a critical application, you need a low TTL, something like 60 seconds, or your automatic failover is going to be painfully slow.
Okay, let's put it all together and start thinking like a senior architect. Knowing the theory is great, but applying it correctly and, more importantly, avoiding the common pitfalls, that's what gives you the architect's edge.
We see these mistakes being made all the time. Number 1, expecting that failover is instant. We just busted that myth. Number 2, using a really high TTL for a critical service, which basically guarantees a slow recovery. Number 3, trying to use a Route 53 health check to monitor a single EC2 instance. That's what your load balancer is for. And finally, a big security risk, putting sensitive internal info on a public health check page.
The best practice here is what we call a layered health model. Think of it like this. You use your application load balancer's health checks for high availability within a region. That's for handling small failures, like one server going down in one availability zone. Then you use Route 53's health checks for big picture disaster recovery between regions. That's for when a whole region goes offline. Different tools for different levels of failure.
This is a really important mental model to get right. When a health check fails, it doesn't magically reach out across the internet and move a user's existing browser session. It's a decision signal. It simply tells Route 53, hey, from now on, give a different answer to anyone who asks for this address. It only influences future DNS lookups.
And look, if you remember only one thing from this entire explainer, please let it be this. You can set your health check to run every 10 seconds, but if your TTL is set to 10 minutes, your failover is going to take 10 minutes. Your recovery speed is dictated by caching, not by detection speed.
So that brings us to the final question, the one for you to think about. Now that you know about the TTL trap and you understand the difference between internal and external health checks, take a hard look at your own systems. How will you go back and re-architect your most critical applications to make them truly resilient?